Go ahead and get started. Good afternoon. Some domain stuff. So we got a couple functions here. F of x is equal to the square root of 16 minus x, and g of x is the square root of x minus 3. We're going to find some domains of, well, first f of x plus g of x. So I would point out here, we need each of these arguments, 16 minus x and x minus 3, to be greater than or equal to 0. In this first one, I would add x to both sides to get 16 is bigger than or equal to x. Or if you prefer, you can write x less than or equal to 16. Similarly, over here, I would add 3 to both sides and get x bigger than or equal to 3. So it looks like we need x to be between 16 and 3. We can also see this graphically. You look at the number line here. And here's 3, and here's 16. And we want to be less than or equal to 16, so left of 16 for the f part, and bigger than or equal to 3 for the g part. So the overlap is exactly everything between 3 and 16 inclusive. So I kind of ran out of room here. The domain for this part is going to be 3 to 16, including both endpoints. Here's the check I like to do after I've done this problem. So cool, I'm pretty sure that's right, but let me do a quick check. If I pick a number just outside of that domain, am I going to have problems? So I pick something like 17, yeah, that's an issue because 16 minus 17 is -1, and we can't take the square root of a negative number. Similarly, if I pick something less than 3, like 2 or 1 or 0, any of those numbers minus 3 is going to be negative, and again, we can't take the square root of a negative number. So I'm feeling good about my answer here. Questions about this one before we do the next number 2 part? So 2 is really not all that different. We still have both conditions needing to be met. The only difference here is that additionally, x can't be 3, right? If we look at the denominator here, if x were to be equal to 3, then we'd have end up having division by 0. So here we want the same as the previous one, but we want to exclude 3. So our domain for this problem is almost the same. It's 3 exclusive all the way to 16 inclusive. I know it's been almost a whole week. It's been 5 days since I saw you all, but last time we met, I did mention how for when you add functions or subtract or multiply or divide functions, all the domains are essentially the same, except when you divide, there's an extra caution we have to take about maybe dividing by 0. On the other hand, the composition of functions can end up with a very different domain than adding, subtracting, multiplying, or dividing two functions. So when we look at the composition of these functions, f of g of x, which is the square root of 16 minus the square root of x minus 3, there's two things I look at, really. I mean, really, we kind of just look overall, but and we don't want to simplify, but I would start with saying, well, I know I have to obey the domain of the inside function here. So we need x minus 3 to be greater than or equal to 0. Or in other words, we still need x to be bigger than or equal to 3. But we don't necessarily need x to be less than or equal to 16, right? In fact, 16 is totally fine. 16 minus 3 is 13. The square root of 13 is, I don't know, between 3 and 4. And 16 minus that number is certainly still positive. So for this larger composition, we have to just look at the whole picture and say, well, we also need the inside of the square root, which is 16 minus the square root of x minus 3, to be greater than or equal to 0. Which means we need whatever we're taking the square root of, this square root has to give us something that's less than or equal to 16. Right? If this was too big, we'd have 16 minus something too big, which would be negative. So what we need is our square root of x minus 3 to be less than or equal to 16. Now, with inequalities, squaring both sides can be dicey, but here it's totally safe. The way I'm going to kind of rationalize it to myself is saying, well, right, if I need the square root of this to be less than or equal to 16, then I need the insides to be less than whatever 16 squared is, which is 256. So we need x minus 3 to be smaller than or equal to 256, which means x has to be less than or equal to 256 plus 3. It's 259. So we got kind of a big domain here. Everything bigger than or equal to 3, all the way up to being less than or equal to 259. And I think we can see that if we plugged in 259, we get 259 minus 3. The square root of 256 is 16. 16 minus 16 is 0. And if you went any larger than 259, this square root here would give an output that was just a little bit bigger than 16, which would be too big for this problem. Let's look at the opposite composition, g of f of x, which is a totally different thing. For g of f of x, is there an open seat anywhere? There's a chair over there you can grab. I don't see any other desks, unfortunately. So for g of f of x equal to this, again, we're going to start the same way. We're going to say that the inside function, the inner square root of 16 minus x, I think it might be, all right, there's another chair over here with your wallet. So we need to obey the domain of the inner function. So we still have x being less than or equal to 16. And then in the same sort of way, we have that the complete insides here, the square root of 16 minus x minus 3 has to be bigger than or equal to 0. So we need this square root, whatever it ends up being, that square root had better be bigger than or equal to 3, which means the insides had better be bigger than or equal to 9. And then subtracting 16 from both sides, negative x is bigger than or equal to 9 minus 16. Multiply both sides by negative 1, x is going to be less than or equal to positive 7. I feel like I'm missing something here. Let's check and see. So first of all, 16 is okay as far as the inner function is concerned, but 16 is too permissive, right? If x is 16, 16 minus 16 is 0, square root of 0 is 0, 0 minus 3 is negative 3. That's a problem. So we actually can't go that high. We have to obey that domain, but sometimes that means being lesser than that. You can grab this chair right here. That's all that's left. So, so we're seeing here that we have x less than or equal to 16. We also have x less than or equal to 7. But I feel like if we go too far, we're going to get, like if we go too negative, we're going to have square roots here that are, I don't know, I feel like I'm forgetting something. 7's fine. I think, yeah, what have I forgotten here? I've forgotten something. Because if I plugged in something like, I don't know, I don't actually know. Maybe not. Maybe I'm just losing my mind. I think I'm just losing my mind. I think I'm totally making myself believe there's more to this than there actually is. I don't think that's the case. I think as long as x is less than or equal to 7, this square root will be big enough so that when you square root it, you're going to get something that's bigger than or equal to 3. I think I was just fooling myself into thinking there's something else here. So here the domain is just negative infinity to 7 inclusive. I don't think we get anything else. I might not sound very convincing because I feel like I almost convinced myself it was the other way. Thoughts? Questions? Yeah. So what I would say is just like over here when we were doing f of x plus g of x, over here we have to have kind of the overlap of the two domains. And so the overlap doesn't get all the way to 16. It's going to end at 7. That's a fair question. Yeah. Good question. What if x were equal to 3? So if I try plugging in 3 here, f of 3 over g of 3 would give me the square root of 16 minus 3, which is 13, over the square root of 3 minus 3, which is 0. And unfortunately, square root of 0 is, well, not unfortunately, the square root of 0 is 0, the square root of 0 is 0, and division by 0 is undefined. So this value here is undefined. And I would say more broadly, when we're talking about domain, the 3 things we look for are potential division by 0, potential taking a square root of a negative number. I should say, these are the things we're trying to avoid. Division by 0, square roots of negatives, and logarithms of 0 or negatives. Yeah, fair question. So where to go next? There's so many things to talk about. Let's talk about inverse functions for a bit. I'll put those over here. If you didn't get this yet, you can just grab it at the end of class. Inverse functions. Let's start off with something really straightforward like f of x equal to 2x minus 1. That's a function, does a thing. Takes an input, multiplies by 2, and subtracts 1. For some functions that are kind of really, well, really for linear functions, but other things as well, it's actually really easy to find the inverse by kind of imagining how to undo what we just did. So if this function takes an input, multiplies it by 2, and then adds 1, we want to undo those things in the opposite order. So I think my inverse is going to be, well, first take my input, undo subtracting 1 by adding 1, undo multiplying by 2 by dividing by 2. Let's check and see if they're inverses. So to check, now I will point out, that's not like the official way of like finding the inverse of a function. It's just a way that works for easy things. We'll talk about like the actual algorithm for doing it in a minute here. But the check here is to check that both f of g of x is equal to x and g of f of x is equal to x. And they are. If we look at f of g of x, that's going to be f of x plus 1 over 2. That's going to be 2 times whatever goes in for x minus 1. And whatever goes in is exactly the x plus 1 over 2. 2 divided by 2 is 1. We get x plus 1 minus 1. And 1 minus 1 is 0. So we get x plus 0, or just x. And then we should check the other direction as well. G of f of x is equal to g of, where'd you get? 2x minus 1. G of stuff is stuff plus 1 divided by 2. And then we're just going to plug that in right there. So we get 2x minus 1 plus 1. Now, I will point out, I've seen people do this before where they just kind of cross everything out that cancels. I really think that's kind of not great to do here because it's unclear if you're canceling things in the right order. So I would first say, oh, the minus 1 plus 1 is 0. I'm left with 2x over 2. And then the 2 divided by 2 is 1. So I get 1x, which is just x. So those are inverses. A couple interesting things about inverses, which I think I mentioned last time, but it was so long ago, I feel like I should say it again. The graph specifically. So if I was going to graph y equal to 2x minus 1, I'd probably graph it by finding both the x-intercept and the y-intercept. The y-intercept is going to be negative 1. And the x-intercept is going to be positive 1/2. And the way we're finding those, right, is our y-intercept, we're setting x equal to 0. We're getting f of 0 equal to 2 times 0 minus 1. For the x-intercept, we're setting y equal to 0, or f of x equal to 0, and solving for x. We get 1 equal to 2x. We get 1/2 equal to x. About right there. I need to find my ruler. I had this really great like 6-inch ruler that I somehow have misplaced. Nope, it's not in there. Oh well, such is life. So then I will point out when we graph the inverse, check out how the x and y things change, specifically the x and y intercept. So for the other function, g of x, the y-intercept is going to be when we set x equal to 0, and g of 0 is 0 plus 1 divided by 2. There's my y-intercept. And then my x-intercept, we're going to set the whole thing equal to 0. Multiply both sides by 2. Subtract 1. We get x equal to negative 1. So the x and y-intercepts have switched, right? For the blue function, the y-intercept is negative 1. For the red function, the x-intercept is negative 1. For the blue function, the x-intercept is 1/2. The red function, the y-intercept is 1/2. So we get this very nice symmetry. Oops, not the right color, James. And I should say further, you can also think of graphing these, or one of them, by reflecting the first one across the line, y equals x. These are mirror images of each other in that line. Let's look at another example. And then we'll talk about how we find these inverses. So let's say we have, where'd you go here? Sure. f of x equal to 2x cubed plus 5. Well, let's talk about how we find the inverse actually. I said that was going to later, but let's do it here. So what you might have noticed from that last example is the x things and the y things interchange, right? Our x-intercepts became y-intercepts, our y-intercepts became x-intercepts. That is not a coincidence. That is because we find the inverse by literally inverting the roles of x and y, or changing x into y and y into x. So typically when I'm finding an inverse, find f inverse of x, we start by first, I like to first write it as y equal to 2x cubed plus 5, or whatever my function is. It's going to be easier to deal with. Some people do this in a slightly different order. Some people like to solve for x first and then switch x and y. I like to switch x and y first and then solve for y. But either way is fine. So the second step, we're going to switch x and y. So x equals 2y cubed plus 5. I will point out at this point, even though we haven't solved for y yet, these things are inverses of each other. I'll point out because I think it's worthwhile to see. I'm not great at graphing those, so let me show you their graphs real quick. Maybe if the internet decides to work, maybe not. So we can graph the cubic function y equal to 2x cubed plus 5, which has kind of, the usual shape. And then if we literally just switch x and y, we don't even have to solve for y. If we just interchange them, x equal to 2y cubed plus 5. Bless you. There's the inverse function. And you can hopefully see, oh yeah, those are definitely reflections of each other in that line y equals x. Every xy coordinate on the red function becomes the interchanged yx coordinate on the blue function, and vice versa. But usually we like to write our inverse functions as functions of x, so we do need to actually solve for y. So that's actually where the real work is done. In the third step here, we're going to solve for y. I'm going to subtract 5 from both sides. I'm going to divide both sides by 2, or multiply both sides by 1/2, however you want to think about it. And then I'm going to take the cube root of both sides. So the cube root of x minus 5 over 2 is equal to y. Or if you're trying to write this in Desmos, web work, y is equal to x minus 5 divided by 2 in parentheses raised to the 1/3 power. Finally, not super necessarily, we do like to use the correct notation, so we could say that our function is f inverse of x and is equal to the cube root of x minus 5 divided by 2. Yeah. So I would make a comment here about how for function and the inverses, the domain and the range interchange because we're literally interchanging the x's and y's. But that's not particularly interesting here because if you look back at the graphs, if I didn't close them, I didn't. We can hopefully kind of see that both the red graph and the blue graph both have a domain that's everything and a range that's everything. I know it's maybe kind of hard to see that for the red graph, the domain is everything, but right, we still keep going to the left and going to the right. There's no issues. Same thing for the blue graph. The range is everything. It does get larger and larger and larger and larger. It just takes a long time to get there. Yes.
Just given the two formulas, can you find the point they intersect at without graphing?
Without graphing, that's a good question. Given the two formulas, can you find a place where they intersect without graphing? So let's see. Let's actually look at this example and see if we can figure it out. I don't know the answer to your question off the top of my head, but let's see if we can figure it out. So if they were to intersect, I think the only place they could intersect is on the line y equals x.
Yeah.
So that means the x and the y coordinate have to be the same. So if our graph is, say, like, for example, if we're thinking of a point on the graph y equal to f of x. That means that point is x comma y or x comma f of x. But those have to equal each other, right? If it's going to be where the two graphs cross each other. So I think the way we do this, and again, this is just what makes sense off the top of my head, I think we have to set f of x equal to x to find the point of intersection. Or f inverse of x equal to x. Either way, if it's solvable, and that might be a challenge, but if it's solvable, that should allow us to find the point of intersection. It's probably challenging to solve here, because if I'm trying to solve 2x cubed plus 5 equal to x, I know there's a solution. I don't know if I know what it is. If I look back at the graphs, it's probably not a very nice number. So, right, yeah, it's some irrational number that we probably would have a hard time finding here. But that's how I think you would go about trying to solve that question if you had a function that was relatively easy to do it for. There was one other thing I wanted to say about these inverses. Let me just double check one thing here. Sorry, I know I'm kind of in the way. I apologize. I wish this would go away. There's something in my way over here, which is super annoying, and it doesn't want there. It goes finally. Sure. Oh yeah, that's what I want to look at. Okay, let's look at one more example here. Maybe ever. I lost it. It went away. All right, my computer is there. You go. Finally. Okay. I had you and you went away. Where'd you go? There we are. So let's look at something like the following. Let's say our function f of x is equal to e to the 3x divided by 4 plus 7e to the 3x. We want to find f inverse of x. The process is the same. So we're going to start with step 1, just writing it as y equal to e to the 3x over 4 plus 7e to the 3x. And really, that's kind of a step you can just skip, right? We know we're going to do that. And then the actual step we need to start with is interchanging x and y. So x equals e to the 3y divided by 4 plus 7e to the 3y. And for a problem like this, what I'm going to try to do is I'm going to try to get all the e to the 3y's on the same side before I deal with just trying to get y. So fractions are always problematic. I want to get rid of that fraction by multiplying both sides by the denominator. X times 4 plus 7e to the 3y equals e to the 3y divided by 4 plus 7e to the 3y times 4 plus 7e to the 3y. Those divide to 1. I distribute the x and I get 4x plus 7x e to the 3y equals e to the 3y. Whenever we're doing a problem like this, if there's multiple y's, we're always going to try to collect them on the same side of the equation, but only the y's and nothing else. So I want all the terms that have y's on the right side, I guess. So 4x is equal to e to the 3y minus 7x times e to the 3y. And then after we've collected all our y's on the same side, we try to factor them out. So I'm going to factor out an e to the 3y. Say we have 4x equal to e to the 3y times 1 minus 7x. Then we can start getting y by itself by dividing both sides by 1 minus 7x. So we're going to have 4x divided by 1 minus 7x equal to e to the 3y. And then finally, to undo an e to the something, we're going to take the inverse function of e to the something, which is the natural log of that something. So I'll point out, we're taking the natural log of both sides. And I'll talk more about this in a minute, but for now, I'll just say that the natural log is just an abbreviation. That ln, natural log of x, is just an abbreviation for the log base e of x. That's all that means. It's just that people typesetting math books use natural log a lot and would rather right, for 2 characters instead of 4 characters when they're typesetting it. So that is one of the reasons why we abbreviate this, because it just comes up so frequently that we don't want to write full letters. It's really based on laziness, nothing else. And it comes up a lot. So then finally, the natural log of 4x over 1 minus 7x is equal to the natural log of e to the something is just the something. And then divide both sides by 3 or multiply both sides by 1/3. So y is going to equal 1/3 times the natural log of 4x over 1 minus 7x. And then finally, if I was writing it as an inverse function, I would say that f inverse of x is equal to 1/3 natural log of 4x over 1 minus 7x. Kind of tricky. I feel like we went down this path last time. The questions or comments before I make you all do one on your own. Yeah. Ooh, I can because I have wonderful tools over here. Yes. So, but yeah, I will be honest, off the top of my head, I don't really know what either of these graphs look like. Let's graph both of them though. So where'd you go? Where did you go? There you are. So graphing the original function, f of x is equal to, we have e to the 3x divided by 4 plus 7e to the 3x. Looking good. Okay, it looks very flat. So let's zoom in a bit just to see here what we've got. So yeah, it's a very not very tall function. It looks like to the left, I would say it probably has a horizontal asymptote of y equals 0. Excuse me. And to the right, I think it has a horizontal asymptote of 1/7. Where am I getting the 1/7 from? From the coefficient of e to the 3x on top being 1 and the coefficient of e to the 3x on the bottom being 7. There's more to say about that at a later date. But if you graph y equals 1/7, you can, yeah, I think I'm pretty convinced that that function is getting closer and closer to 1/7 and it's probably never actually crossing it. It's not the most beautiful function I've ever described. On the other side, let's look at the inverse function. Let's call it g of x. And g of x is going to equal what we got for the reverse, which is 1/3 natural log of 4x divided by 1 minus 7x. And yeah, that certainly in this close-up window here, it looks very much like they're inverses of each other. And if we zoom out a little bit, yeah. So I'll also point out, you can very much see that f of x has a very limited range and g of x has a very limited domain. And they're the same as each other. So I'm going to write this down here while I'm looking over here and then you guys can see it. So I would say that the domain of g of x appears to be everything from 0 exclusive to 1/7 exclusive. And it's the same as the range of f of x, which is from 0 to 1/7. That looks not the best. Let me brighten that up for you. That seems better. And similarly, the domain of f of x is everything from -infinity to infinity, and it's the same as the range of g of x. That was a little sloppy down there. Which actually brings me to a really important point. When you find the inverse of a function, the domain and the range are interchanged. Because the domain is all the x things, the range is all the y things, and if we interchange x and y, we're interchanging the domain and the range. So what that means is if we're asked to find the range of a function and the function is invertible, we can find the domain of the inverse to find the range of the original function. Let me show you an example of this. Let's say we want to find the range of f of x equal to 6x minus 1 over 2x plus 4. I guess I could have factored out the 2 from the bottom, but I didn't. All right, let's see what we get. So we're going to find the inverse. So find f inverse of x. Okay, so I'm starting with y equal to 6x minus 1 over 2x plus 4. I'm changing there should only ever be one y. I'm changing the only y into an x. I'm changing all the instances of x, which there could be more than one of, into y's. I guess I could number by step. And now for the hard part. We're going to solve for y. So I'm going to, just like in the previous problem, actually, I'm going to multiply both sides by the denominator as my first step. I almost never want to have denominators in my equation if I can help it. So if I can ever get rid of them, I will. X times 2y plus 4 equals 6y minus 1. Distribute the x. I get 2xy plus 4x equals 6y minus 1. Collect all the y things on one side and everything else on the other side. It doesn't really matter which side you pick. If you end up picking the opposite sides I pick, your answers will look almost the same as mine, except the top and bottom of your fraction will both be the opposite signs of what I have. But they'll still be right. I'm going to bring my y's to the left, to the right. So I'm going to have 4x plus 1 equal to 6y minus 2x times y. Factor out the y from the right-hand side. We're left with y times 6 minus 2x. Divide both sides by 6 minus 2x to get 4x plus 1 divided by 6 minus 2x equal to y. So my inverse function is equal to 4x plus 1 over 6 minus 2x. And we can fairly easily see that the domain here of f inverse, well, we're going to exclude whatever makes the denominator equal 0. So we're going to exclude when 6 minus 2x is equal to 0. Or in other words, when x is equal to 3. Sorry, that's terrible. So our domain here is, so the domain of f inverse, which is equal to the range of f of x, is everything except for positive 3. Let me offer you some proof. So what we've said here is this function can equal any number except for 3. Right? You can't get 3 as an output. You can get anything else, but you can't get 3. So what if we tried to get 3? If we set this equal to 3, look what happens. I'm going to multiply both sides by 2x plus 4. I'm going to 6x minus 1 equals 3 times 2x plus 4. Distribute. 6x minus 1 equals 6x plus 12. Subtract 6x from both sides, and you get negative 1 equal to 12, which is not true. So this function couldn't ever equal 3 because that results in saying something that isn't true. And you can't get any other value. But I do want to emphasize here, that's often how we find the range of a function, is by finding the domain of its inverse function, if that's possible. I should say, if the function's invertible, because not every function is invertible. Yeah, we'll talk about inverses for a few more minutes here, and then we will move on. So one more function that's kind of interesting. What about f of x equal to x squared plus 3? Meaning, is there an inverse? Well, I should be more explicit here. Is there an inverse function? And unfortunately, the answer is it depends. Depends on how you want to think of things. Depends on what your teacher wants you to do. So let's kind of look at the whole picture here. Here's my graph of f of x. X squared plus 3. It's my usual parabola shifted up 3 units. And then if I were to graph the inverse relationship, I would just reflect it across the line y equals x, or I could literally interchange x and y. If I take y equals x squared plus 3 and interchange the x and the y and don't do anything else, my inverse relationship has a graph that's x equal to y squared plus 3, which is a rightward opening parabola. Which is not a function, right? This thing I just drew fails the vertical line test. X equal to y squared plus 3 is not a function. Specifically, it's not a function of x, right? When we say something is or isn't a function at this juncture, we mean specifically that x is the input and y is the output. So this is not a function of x. But that's not the end of the story. We could just leave it there and say, yes, this function is not invertible, but we could do more work to make it so it is invertible. So what we typically do for functions that aren't invertible, that we still want to have an inverse for, is we restrict their domain. We say, well, this original function, if it were to pass the horizontal line test, which it doesn't currently, just like this doesn't pass the vertical line test, we can restrict it to say just the right half. In other words, we can say if our function f of x equal to x squared plus 3 is restricted to where x is greater than or equal to 0, then the new thing we're talking about is just the right half of this parabola, which is 1-to-1, also known as passing the horizontal line test, also known as being invertible. And its inverse is, well, I'm going to draw it first. It's just this top half. Here's how we're going to find the inverse. And this, I feel like this is where things get kind of weird. So we're going to start with y equals x squared plus 3. And we're going to remember that x has to be greater than or equal to 0. And now when we find the inverse, we're going to interchange all the x's and y's. So my inverse is going to be x. I meant to use a red pen there. X equal to y squared plus 3. And we're restricted to y being greater than or equal to 0. I said all the x's and y's. I meant all the x's and y's. And then if we solve for y here, we get x minus 3 equal to y squared. And then when we square root both sides, normally we would say that y was equal to plus or minus the square root of x minus 3. This is the plus part. This is the minus part. But we don't need or really even get the minus part because we've said that y can't be negative. Y has to be positive. So here our inverse function is y is equal to, apologies, the positive square root of x minus 3. Kind of interesting. Or writing it in the final notation here, my f inverse of x is the square root of x minus 3. But it required us to do some stuff, right? We couldn't just, you can't just say that this original function is invertible. It's not. You might actually kind of be curious about what happens if we, so I'll say one more thing about this example, and then we will move on. So if we had, no, I don't love that. Yeah, I want to say something slightly different. Sorry for making it kind of weird here. But I just want to point out, note that f of x equal to x squared and g of x equal to the square root of x. If I don't mention any domain restrictions, without domain restrictions, are not inverses. What I mean by this is, let's look what happens if we compose these functions with each other. So for f of g of x, that's f of the square root of x, which is the input squared. And when you take a number x, well, x already has to be non-negative, right? Because that's the domain of the inner function. And you square the square root, you do just get x, right? If x was 9, the square root of 9 is 3. 3 squared is 9. And for any input we're allowed, we're going to get the same output. But the other direction doesn't go as well. If we look at g of f of x, which is g of x squared, which is the square root of the input, the square root of x squared isn't just x. We've seen a couple of times here that this actually leads us to the absolute value of x, which is not equal to x all the time. And that's how we are seeing that these two functions, if we don't do anything with them, don't actually end up being inverses of each other. Because here you could input some negative value for x and end up with not the same thing at the very end, which is kind of a problem. So I'll point out here, right? If you look at, say, like g of f of -3, you get g of -3 squared, which is g of 9, which is the square root of 9, which is 3, which isn't what we started with. So that shows that these functions are not inverses of each other without doing more work to restrict the domains. Okay. Probably said more on that than I really needed to, but not bad to see it. Just there's so many other things to talk about. All right. So the last kind of pair of inverse functions I wanted to mention are the logarithmic and the exponential functions. So logarithms and exponentials are inverse functions by design. So, for example, f of x equal to 3 to the x and g of x equal to log base 3 of x exactly undo what the other one does. And really, that is the word I would like you to associate with inverse functions, is they undo each other. One of them does something, the other one undoes it. In this case, for example, f of 2 is 3 squared, which is 9. G of 9 is log base 3 of 9. And when we write that, the words I say in my head are 3 to what power equals 9? And the answer is 2. We ended up back where we started. We started with 2. We did f and we got 9. We did g to that and we got back to 2. So logarithms and exponential functions are inverses of each other. And there's a few graphical things we should see. So many things. So let's graph them. We're going to graph f of x equal to 3 to the x and g of x equal to log base 3 of x. And all I'm really going to do is I'm going to plot a few points for f of x, and then I'm going to invert all of them to get the points for g of x. So here's my table for f of x. Make like 5 points. Here's my x value and my 3 to the x. So if x is, say, 2 or 1 or 0 or -1 or -2, 3 squared is 9. 3 to the first is 3. 3 to the 0th is 1. 3 to the -1 is 1 over 3. 3 to the -2 is 1 over 3 squared, which is 1 over 9. So let's see. I'm going to try to make this look fairly decent. There's a high of 9. Let's see. I get the point 2, 9. Let's use a nice color like blue. and 1 comma 3, 0 comma 1. These points to the left always seem like they're a little challenging. -1, 1/3, -2, 1/9. So this function has the usual exponential shape. And then for the logarithmic function, I'm gonna pretend like I'm writing down the table, but I'm really not. I mean, I am, but like what I'm really doing is actually I'm looking at my previous table and I'm just switching everything. So instead of having 2 and 9 as the input and output, my input and output are 9 and 2, and then 3 and 1, and then 1 and 0, and then 1/3 and -1, and then 1/9 and -2. Just to make sure everyone's on board with that, right? It really is true that if you plug in 1/9 for x, log base 3 of 1/9 has to be -2 because we're just looking for the power on 3 that makes it equal to the argument 1/9. So graphing this, we're going to have the same but opposite points. I knew I was doing myself a disfavor when I made this kind of large. 4, 5, 6, 7, 8, 9. Sorry, my x-axis is a little bit more spread out than my y-axis. Take the point 9 comma 2, 3 comma 1, 1 comma 0, 1/3 comma -1, 1/9 comma -2. And so here is our, okay, here's our graph. Okay. That looks okay. Not the best I've ever done. And these two functions have all the same properties except switched. So for our f of x equal to 3 to the x, our domain is everything. Our range is all positive numbers. We have a horizontal asymptote at y equal to 0, and we have a y-intercept at 0 comma 1. For the other function, for the inverse function, g of x equal to log base 3 of x, everything switches. So my domain is everything that's positive, 0 to infinity. My range, even though it looks like it takes forever, technically it does, right? This function does keep getting larger and larger and larger. It just feels like you're like, it could flatten out. It never flattens out. It keeps getting larger and larger. The range is every real number. The vertical asymptote is x equal to 0, and the intercept is an x-intercept of 1 comma 0. And again, notice, I know I've said it like 1,000 times, but again, notice all of the x and y properties have interchanged with each other. Any x thing over here is a y thing over there, and any y thing over here is an x thing over here. Okay. Yeah, we should start going that way. Sure. I know last week we talked a little bit about exponential growth and exponential decay. Well, actually just growth. We didn't talk about decay. They're really kind of the same thing, but I did want to throw one more example at you in that direction. So let's look at an exponential decay problem. So here's an example. The half-life of some element, bismuth, I don't know how to pronounce that, bismuth, 210, is 5 days. How much of a 200 milligram sample remains after 3 weeks? And before we answer this kind of the long way, we'll do this kind of, we'll get an idea of what our answer should be. So what does it mean that the half-life is 5 days? It means that, oh yeah, go ahead.
Every 5 days, the sample halves in size.
Exactly.
Right.
Yes. So exactly what he said. I don't think I need to say it again. Let's make a little table here just to kind of see what's happening. So we'll have our time on the left and our mass at time t on the right. So in the beginning, on day 0, we have 200 milligrams to start with. And then after one half-life period, so after 5 days, we're going to have half of that. So we're going to have 200 times 1/2, which is going to equal 100. After another 5 days, so 10 days total, it's going to be 200 times a half, which is going to be 100 divided by 2, which is 50. And finally, not finally, but after 15 days, it's going to be 200 times a half, which is going to be 25. And then I guess we could do one more. For 20 days, we're going to get 200 times 1/2 to the 4th, which is going to be half of 25, which is 12.5. So we're expecting that after 3 weeks, well, 3 weeks is 21 days. So we should be pretty close to that value there, maybe just a little bit less than 12.5 grams left. So how are we going to do this? Well, there's a couple ways to do this, and I don't really know which way is preferred. So I'll talk about both, even though, well, I'll do the way I think is preferred first, and then we can talk about the other one. So I would point out that every time we increase the time by 5, we're going to increase this power by 1. So if I said we wanted to figure out how long or how much we had after, say, 100 days, well, that would be 200 times 1/2 to the what power? Yeah, exactly. The 20th power, because 20 is 5, sorry, 100 is 5 20 times, or 20 increments of 5. So it looks like this power here is always the number of days divided by 5, right? 1 is 5 divided by 5, 2 is 10 divided by 5, 3 is 15 divided by 5. So I feel like we could make our growth model to be 200 times 1/2 to the t divided by 5 power. And that seems like it tracks, right? If we plug in any of these values, we're going to get exactly this output that we got here. So to answer the question, if we want to know how much remains after 3 weeks, which is 21 days, that's going to be 200 times 1/2 to the 21 divided by 5. Which I didn't write out, so let's see what we get. That's not where I want to do that, because I actually want to get a number here. 21 divided by 5 is 4.2. So we get approximately 10.88 milligrams, sorry. Which seems reasonable based on what we've already done, right? 20 days got us down to 12.5 milligrams. So it seems plausible that another day would get us down to 10.88, right? We're certainly not out of the realm of plausibility. Yeah, I feel like that's kind of so there is another way to do this, but I feel really like for this class, the intent is to kind of think of it more this way. So there certainly is another way you can do this, where you start with something like A of t equals C e to the kt, and then you use some data points to find your C and your K. I'll point out that if we plug in t equal to 0, our A value is 200, so we get 200 equal to C e to the K times 0. K times 0 is 0. E to the 0 is 1. So C times 1 is 200, which gives us C equal to 200. To find the K value, you have to pick one of these other points. So if I was going to plug in, say, like T equals 5 and A equals 100, I could plug in that and get 100 equals 200 e to the k times 5, and then solve for k. Divide both sides by 200, so 1/2 equals e to the 5k. Take the natural log of both sides. The natural log of 1/2 equals the natural log of e to the 5k. The natural log of e to the 5k is just 5k. So the natural log of 1/2 equals 5 times k. And so then we get 1/5 times the natural log of 1/2 is equal to my k value. And then finally, if we wanted to, we could rewrite the model as A of t equal to 200 times e to the 1/5 natural log of 1/2 times t. And although, and I think I said this last time, although it doesn't quite look like it, I will tell you that this is exactly the same as this. And I think at least it seems like it was easier to come up with this than it was to come up with this. This feels relatively straightforward if we make this table and kind of just see how much t has to increase every time to increase our power by 1. But you're welcome to do it either way. All right, here's where we're going. I can find my notes. Notes everywhere. So one of the reasons we're spending kind of a bit of time talking about exponential and logarithmic things is because we're going to do some graphing with exponential and logarithmic kind of utility. What do I mean by this? Well, let's look at the following example. So we're moving into talking about, semi-log, also called log linear, and log-log plots. So let's graph the following. Y equal to 3 times 5 to the x. Let's plot a couple points here. So if x is 0, y is going to equal 3 times 5 to the 0, which is 3 times 1, which is 3. If x is 1, y is going to equal, why am I writing y here? I don't know. Sorry about that. 3 times 5 to the first, which is 15. X is 2, we're going to get 3 times 5 squared, which is 3 times 25, which is 75. Let's go a couple more here. X is 3. We're going to get 3 times 5 to the third, which is 3 times 125, which is 375. And things get out of control pretty quickly here. If x is 4, we get 3 times 5 to the fourth, which is 3 times 625, which is 1,875. So not even getting up to x equal to 10, we've already got y values that are vastly outpacing our x values, right? We try to graph this. The graph doesn't really say a whole lot to us other than, yeah, it's exponential, right? And certainly if we were to graph this, right, we could plot x equal to 0, y equal to 3, and it's going to do something like this, but it's going to get, super big, super fast. It doesn't really help me see what's going on. So one thing we do when our functional relationship is exponential in nature is we're going to turn it into a logarithmic, or I should say we're going to take a logarithm of both sides and then graph the x values. Instead of graphing the y values, we're going to graph the log of y values because they are going to be much less extreme. Here's what I mean. So if we start with y equal to 3 times 5 to the x, we're going to take the log base 10 of both sides. And I think I failed to say this, but I'll point out. So if we take the log base 10 of both sides, and so just as a quick note over here, just like the log base e of x is abbreviated as the natural log of x, hopefully all of your teachers are abbreviating this way. Sometimes, unfortunately, people abbreviate the natural log of x with just an log of x. Yeah. Yes, I can. Thank you. But usually in this class, people abbreviate the natural log as ln of x. And then the log base 10 of x often gets abbreviated as just log of x. That is a 10 there, believe it or not. A few things to be aware of. The natural log of e is equal to 1, because we're saying e to what power equals e. The log of 10 similarly is equal to 1. The natural log of 1 is equal to 0. The log of 1 is equal to 0. So the idea here is we're going to take this equation and we're going to rewrite it using some of our rules of logarithms. So I have the log of 3 times 5 to the x. I can rewrite that as the log of 3 plus the log of 5 to the x. And then using another log rule, I can bring this exponent down in front of log of 5. This is really equal to log of 3 plus x times log of 5. So what we've got here is the equation. I'm going to rewrite it just slightly. This log of y is on the left-hand side. What we have is log of y equal to, I'm going to rearrange the order here. I'm going to write it as log of 5 times x plus log of 3. Or what I really want you to see is we usually call the log of y as capital Y equal to some slope times x plus some y-intercept. So we're turning this new thing into a linear kind of function. So the log linear graph here of the original y equal to 3 times 5 to the x given by capital Y equal to log 5 times x plus log of 3. Oh. And I think I forgot to bring something kind of important, which is unfortunate. So the idea here is that on our x-axis, we have regular x, but our y-axis is no longer regular y. It's the capital Y, which is equal to log of regular y. And it's going to look like the following. Trying to think what log. Let's see, what's log of 5 and log of 3? One moment. Just so we can make this look somewhat decent here. Log of 5 is approximately, wow, that's interesting. Fine. Point 0.7. And log of 3 is approximately 0.26. So our graph looks something like this. Got a slope of 0.7. It's got a y-intercept of 0.3. So it's about like, again, I'm kind of eyeballing it here. So these are typical x values, but these are capital Y values, meaning they correspond to much larger actual output values, right? If capital Y is 1, regular Y is 10. If capital Y is 2, regular Y is 100. Capital Y is 3, regular Y is 1,000, and so on and so forth. So we're representing the same relationship. It just looks very different, but it looks more manageable. I don't have any semi-log paper with me, and I don't imagine you're actually going to be probably asked to use it. But there is graph paper where like the x-axis shows like a regular like normal gradation of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whereas the vertical axis shows lines that are kind of written differently because they're representing logarithmic values instead of just the actual values. I would say the takeaway here is that exponential functions, that is something like y equal to c times b to the x, are linear on a semi-log graph. let's look at another different example that has a similar thing happening, but not quite the same. Sorry, one moment here. And we'll kind of talk about how to manage this. So let's look at something else. Sorry, where'd you go? Let's now look at the graph of, say, y equal to 5 times x to the fourth. Here we do need to say that x is greater than 0. Again, we'll make a table. So if x is 1, y is going to be 5 times 1. If x is 2, y is going to be 5 times 2 to the fourth, which is 16. So 5 times 16 is 80. X is 3, 5 times 3 to the fourth, which is 405. Things are getting out of hand rapidly. 5 times 4 to the fourth is, good question. What is 5 times 4 to the fourth? It's big. It's 1,280. So things are once again getting out of control, right? This graph is polynomial. It looks kind of like this. But again, this graph doesn't really tell us a whole lot, other than things get big fast. But if we want to know more about the relationship, we're again going to look at taking the log base 10 of both sides and doing a similar thing with a slightly different result. So we're going to take log of both sides. So we're going to have log of y equal to log of 5 times x to the fourth. And we're going to use the same logarithmic rules we used before to break this apart so it looks like some sort of linear equation. I know it's not linear, but we're going to make it look linear. So we have log of y equal to log of 5 plus log of x to the fourth. We're going to bring the 4 down in front. We have log of y equal to log of 5 plus 4 times log of x. For no reason other than I think it looks nicer, I'm going to rearrange this slightly and say it's log of y equals 4 times log of x plus log of 5. And in this example, our log of y is going to become capital Y again. Wow, that's a y, James? Sure, we can pretend that's a y. Sorry about that. And log of x is going to become capital X. This coefficient here is our m, and this is our b. We get y equals some mx plus b. But here, it's not semi-log, right? We're not just using the log of y. We're also using the log of x. So this is going to be log log. So this relationship, this power function, y equal to 5x to the fourth, called a power function because it's x to a power, is linear on a log-log graph. Which might feel kind of weird to even think about, to be honest. Like, I will fully admit, the first time I saw this when I was teaching this class a couple years ago, I was like, what do we do? Why are we doing this? This seems very kind of, I don't know, it felt just kind of unnecessary, right? Like you're doing this whole extra thing, and then what are you doing with it? I don't have a good answer to that question. I do know that your teachers are going to teach it most likely, so we need to cover it. But as far as like, you're not wrong to feel like this feels kind of like we're taking the longest, hardest route to get somewhere. We kind of are. That said, it is kind of interesting. Let's look at a couple examples. Let me grab one over here. I think we'll have enough time for that. Yeah. Sorry, 1 second. Yes.
If you didn't have x is greater than 0, would this graph be a upward of a parabola?
Well, yes, but so the reason why I'm specifying that x is greater than 0, though, is because to be able to take the log of both sides,
Yeah.
I can't take the log of something that's, well, in fact, so right, x being, yeah, I mean, it's actually not problematic here, but like right here, this log of x is problematic if x is negative. So that's why, but you're right. It would look It's actually not technically a parabola because it's x to the fourth, but it has a similar look to a parabola. But specifically, parabola is the name for a polynomial of degree 2.
Okay. Does every polynomial have its own name?
Not really. So like it's like y equals 3x plus 1 is a linear function. Y equals ax squared plus bx plus c is a quadratic or a parabola. Y equals x cubed is a cubic function. But after that, the names kind of become meaningless. Like you could call x to the fourth a quartic, but there's no good reason to do that. So let's look at an example of how you might kind of be asked to apply this. And I'll show you one kind of written out, and then we'll try to do one using some other stuff. So let's say the following. Suppose there's gonna be a lot of words here. Suppose that we follow a population over time, and when we plot our data on a semi-log plot with base 10, a straight line with a slope of 1.2 results. Furthermore, assume that the population size at time 0 was 50 people. What function best describes the population size at time t? All right. Kind of weird. So a couple ways to think about this. Thing one, the first thing I noticed is that they told me that we had linear data on a semi-log plot. To me, that automatically rings a bell that, oh, I know my end result here, the function should be exponential, meaning I should have something raised to the t power, not something like t to the fourth. I have like 3 to the t or something like that at the end of the day. There's a couple ways to approach this. Just thinking graphically for a second, although I don't really need the graph here. It's semi-log, so our horizontal axis is just the regular x, or in this case, I would probably use t variable. And our vertical axis is not the regular y, it's the capital Y, which is the log of little y. And they said the line looks something like this, right? The slope is 1.2. And let's be really careful about reading the words here. They didn't say that the y-intercept was 50. They said that at time equals 0, the population is 50. Meaning the little y value is 50, not the big y value. Right? The little y value is our population. So little y is the thing that's being measured, is our population. Big Y is the log of that. All right, I think we can write this equation. So I'm going to start off by saying, well, just writing the equation of this line, it's capital Y equal to mx plus b. Just as a starting point. I know the slope is 1.2. I'm not so sure about the b value yet, but I know over here on the left-hand side, I'm going to replace capital Y with log of y. B plus b. I suppose I could plug in my values to find the b, right? If I plug in 0 for, I used x when I meant to use t. Sorry about that. Well, we're using x now. I should have used t, but I didn't. Sorry. So if I plug in y equal to 50 when time is equal to 0, I'm going to get log of 50 equal to 1.2 times 0 plus b. So yeah, my b value is not 50, but log of 50. So that's my intercept on the semi-log graph. That point there is 0, comma log of 50. So I would say if you see a problem like this, be careful when you read it about whether they're saying you have a y-intercept or an amount of stuff at time equals 0, because they mean slightly different kind of things. One is talking about the point on the graph. One is talking about the y value before you've taken the log of it. So then we can say we've got log of y equal to 1.2 times x plus log of 50. And now our job is to figure out what y is. So we're going to undo the logarithm. So whenever you're trying to undo a logarithm, you're trying to essentially raise both sides to a power that is the base. Like when we had that natural log of something we were trying to undo, we raised both sides as powers of e. Here we're going to write both sides as powers of the common base, which is 10. So we're going to rewrite this as 10 to the log base 10 of y equal to 10 to the 1.2x plus log base 10 of 50. I know I'm not writing the base 10, but I'm saying it so you remember that it's actually there. 10 to the log base 10 of y is y. On the right-hand side, we do a couple things. We break it up as 10 to the 1.2x times 10 to the log of 50. 10 to the log of 50 is just 50, right? Those are functions that undo each other. 10 to the power of something and log base 10 of something undo each other to get 50. Why does that work that way? I know we only got like 3 minutes, but let me just point out real quick. I know we're almost done with this, but let me point out something kind of worthwhile, I think. Why does 10 to the log base 10 of 50 equal 50? Well, kind of because it has to. But really, let me phrase it in a different way. What's log? This is my favorite. Log base 2 of 8 is my go-to for logarithms. What is log base 2 of 8? Or 2 to what power equals 8? 3, right? So now we're going to say 2 to the power that you raise 2 to get 8 should be 8, right? If this is the power that you put on 2 to get 8, and you're putting it on 2, you should get 8. Similarly, if this number, whatever godforsaken number this is, it's something terrible like, I don't know, 1.7, probably smaller than that. But whatever number that is, it's the number that you raise 10 to get 50. Well, we're raising 10 to that number. We better get 50. There's no other option. So that's why you can kind of talk it out to yourself and say like, well, it has to be this way because you're raising this base to the power that you exactly raised that base to get the result that you want. So that's why 10 to the log base 10 of 50 equals 50, or why any base to the log base b, the same base of whatever thing you want, is just going to be that. That's why. So back to this, we're almost done here. We want to then write this, well, 10 to the log base 10 to 50 is just 50. So we're going to rewrite this as y equal to 50 times, and now we're going to do one more thing. Instead of writing it as 10 to the 1.2 times x, usually we prefer to write it as 10 to the 1.2 to the x power. I don't think there's really a great reason for doing that, but we want to really exemplify the fact that it is an exponential function. So it's some constant times some base 10 to the 1.2 power raised to the x. So that is our relationship. So I would say that y as a function of x, not t as I was about to write, is exactly 50 times 10 to the 1.2 to the x power. And we didn't get to the other thing, but we will get to it on Thursday. So on Thursday, we'll talk a little bit more about this, and we'll also talk about how you can take a bunch of data, plot it in Google Sheets, and then try to determine if that data is going to either have a linear semi-log relationship or a linear log-log relationship, and kind of the process for doing that, which isn't as terrible as it sounds. And there already is a video on Canvas of me doing that. If you're already there in your class, you need to see it. There's a video on Canvas that you can check out.